All right, let's talk about one of the biggest, most mind-bending discoveries in modern physics. We're going to dive into a particle with a name so huge it sounds like it's straight out of mythology, the God particle. But what is it really, and where in the world did it get that name? Let's get into it.
Yeah, this is the big question, right? It's the name that captured everyone's imagination. It sounds like it should be the ultimate secret to the universe, some all-powerful thing. But the real story behind that name? Well, it's probably not what you're thinking.
And there it is. The origin story wasn't about divinity at all. It came from a place of pure, head-banging against the wall frustration. You see, Nobel laureate Leon Lederman wanted to call his book The Goddamn Particle because it was just so ridiculously hard and expensive to find. His publisher, for obvious reasons, thought that was a bit much and just shortened it.
And, that one little marketing tweak, it created this huge myth that physicists have been trying to clear up ever since. Because the name, the God particle, it kind of gets the science completely backward.
So here's the most important thing to get straight. The myth makes you picture the single, super powerful particle, but the reality is so much bigger, so much more profound than that. It's not really about the particle at all. It's about an invisible, universe-spanning field. The particle we found is just a proof that the field is real.
Okay, so let's shift our focus to the real star of the show here, the Higgs field itself. This is the concept that really truly changes how we understand reality.
You have to wrap your head around this. The Higgs field isn't in the universe. In a very real way, it is the background hum of the universe. It's been everywhere, since a split second after the Big Bang. Unlike other fields, its default energy state isn't zero. It has this constant value everywhere, just a property of empty space itself.
So how do you even picture something like that? Well, the best analogy by far is to imagine that all of space, the entire universe, is filled with a kind of invisible cosmic ocean. It's just there, always.
And that little ripple? That's the Higgs boson. It's just a tiny, momentary splash in that great big ocean. Finding that ripple, that particle, was the only way we could prove that the entire ocean was there in the first place. The particle is the evidence, the field is the reality. So, how does this field give things mass? Okay, imagine you're at a cocktail party. The room is full of people, spread out evenly. That's the Higgs field. Now, if some random person walks through, they can just move right through, no problem. That's like a massless particle, like a photon of light. But then, a huge celebrity walks in. People flock to them, slow them down, make it harder for them to move. That resistance, that drag, that's mass. And the Higgs boson, that's like a rumor spreading through the party. A little clump of people that moves through the room. It's an excitation of the field itself.
Now get ready for a mind bender. This field, it's only responsible for about 1% of the mass of all the stuff we can see around us. Just 1%. Most of the mass in you and me comes from the energy holding our atoms together. But, and this is absolutely critical, that tiny 1% is the foundation for everything. Without it, electrons would be massless. They'd just zip around at the speed of light, and they could never settle into orbits around a nucleus. No atoms, no stars, no us. The entire universe would be impossible without it.
And figuring all this out, well, it kicked off one of the greatest scientific quests in human history. It spanned generations of scientists and led to building the most complex machine humanity has ever conceived.
I mean, look at this journey. It all started back in 1964 with these theoretical papers. And can you believe it? Peter Higgs's paper, the one that specifically predicted the particle, was actually rejected at first. It took nearly 50 years, a massive global effort to build a Large Hadron Collider, before that day, July 4th, 2012, when the discovery was finally announced. Peter Higgs himself was sitting in the audience, and you can see photos of him wiping away a tear. He lived to see his theory proven right.
And the scale of this challenge? It's just hard to even comprehend. They were hunting for a particle that exists for less than a trillionth of a second, and it only shows up in about 1 out of every billion collisions they create. It was like trying to find one specific, unique grain of sand in the middle of a hurricane.
So after all that effort, after decades of searching, what did we actually find? Let's take a look at the portrait of the Higgs boson that scientists have so carefully pieced together.
Its mass has now been measured with incredible precision. It's about 125 giga-electron volts. Now, that's not just some random number, it's a brand new fundamental constant of nature. And here's the wild part, maybe even a little chilling. That specific value, when you plug it into our equations,
suggests that our entire universe might only be temporarily stable, existing in what's called a false vacuum.
This chart lays out its basic stats, but the really unique thing here is the spin. The Higgs boson has a quantum spin of 0, and that might not sound like much, but it makes it completely unique. Every other fundamental particle we've ever found has spin. The Higgs is the first and only scalar particle, a particle with no intrinsic spin ever discovered. It was a massive confirmation of the theory.
You see, finding the Higgs wasn't the end of the story, not even close. It was the beginning of a whole new chapter. It didn't just answer a question for us, it gave us a brand new tool to ask even bigger, even weirder questions.
So its first, most immediate job was to complete what we call the Standard Model, our absolute best theory of how the subatomic world works. For decades, this whole theory was built on the assumption that the Higgs mechanism was real. Finding the boson was like slamming the final keystone into place, locking the entire magnificent structure together. It works. But now the Higgs has gone from being the thing we hunt to being the hunter. Physicists are using it as a probe to explore the deepest mysteries out there. Things like, could the Higgs interact with dark matter, acting as some kind of portal to that hidden universe? Does its mass really mean our universe is living on borrowed time? And maybe the biggest question of all, did the Higgs field itself play a role in why there's more matter than antimatter, which is the only reason any of us are here to ask these questions?
And that's really the big takeaway. The search for the Higgs boson is over. That quest is complete. But the exploration of the universe it has unlocked, that has only just begun. It has completed our map of the known world, but in doing so, it has also sharpened the boundary between what we know and all the vast, dark, unknown territory that still lies beyond.